Okay. Yes. As we start there, I'll start by, of course, asking these children to let us know. I know they have a lot of knowledge, a lot of information. Some have read ahead, but also they bring a lot of experience from primary about some of these things that we're talking about. So I want somebody to tell us when we hit a solid, if you start off with ice and you hit it, this ice will change into something. Somebody will be helping us know what that process is called, and then we pick it from there. So who can tell us the name of a process involved when ice converts to a liquid, or as a solid is changed to liquids? What name would we give to that process?
Okay, I can see we have a tendotamali.
Okay.
The process by which a solid turns into a liquid is called melting.
It's called melting. Thank you very much. Yes, we call it melting. And this normally happens at a certain temperature. I may want to know who can tell us what the name of that temperature at which that process takes place is called.
Okay, Mutamba.
Melting point.
It's called melting point. Thank you very much. Okay. Anybody tell us what the melting point of ice is?
Above 1.
Charlie, it is there.
0 degrees. Wait.
0 degrees Celsius for ice. Okay. Is there anybody who can tell us what brings about that melting? What way causes the melting to happen?
Increased heat.
What do you think? Starting from where we came from, remember you said that solids, there are forces of attraction that exist between a solid, and when you hit these solids, something happens. So can we know what do you think is likely to cause that melting? Somebody, let me see, Mr. Sari.
Yes, I can. We can have here Crown and Mutant share.
Yes, teacher.
Yes, please go ahead.
Teacher, I think that melting is caused by the heat gain the solid gets.
I didn't hear you very well there. Could you please come again?
I think it's caused by the heat gain the solid gains. The heat the solid gains.
The heat the solid gains. Okay, thank you. What I'm trying to get to is when this heat is absorbed by the solid, what does it actually do to the solid in order to bring about that melting? I want somebody to tell us what happens. Yes, Mr. Sari.
Crown seems to be there. She wants to.
Yes, teacher. The particles separate. When the solid gains heat, the particles separate.
The particle separates. So there's some kind of, so when you say separation, I think you're trying to say that they move a little bit apart. Okay. Yeah. What is that likely to do to the forces of attraction between the solids particles or between those particles? They become
weak.
They become weak. Okay. Thank you very much. Mr. Sanjay, you had talked about sharing the notes.
I shared the notes, but I'm wondering why.
Probably because
I think you remove your serif.
Okay, I get out of the meeting. Okay, sir.
The notes are there.
I can see. Okay, thank you very much, Mr. Senjove. I can now see the notes very clearly. So the girls have told us that when you hit a solid, first of all, if you keep hitting a solid, from what we've had there, our default saying, the particles move adrift, they move other parts, and consequently, this leads to a decrease in the forces of attraction between the particles. So if you progressively do this, we expect continuous separation to keep happening, consequently leading to weakening and further weakening of the forces of attraction. And certainly, if that continues, then we are likely to see the forces completely becoming too weak, and consequently the solid structure beginning to collapse, hence leading to that process referred to as melting. Yes.
Mr. Chairman.
Yes, sir.
Actually, that subtitle which you see there, we had read it in the last lesson. Maybe
Okay.
it's just a reminder. We did it in
Yes.
the last lesson so the girls can read through, and
Okay.
then we start from there.
Yes, we were kind of doing a recap of the
Yes,
previous
this is a
stuff that
recap of what happened. Yes.
Okay. Okay. Anybody wanting to ready to read for us that bit there as we move forward?
Okay, Adeke, you are the first to put up the hand. May you unmute and read for us?
Okay. What happens to particles in a solid when they are heated? Look at figure 3.4, which shows the arrangement of particles in a solid, a liquid, and a gas. In a solid, the particles are arranged in lines next to each other. You know that when you heat a solid, such as ice, it will turn into a liquid. When you heat a solid, you are giving it energy. The energy is heat energy, and it makes the particles in the solid vibrate faster. The heat energy is turned into movement energy of the vibrating particles. If the particles are given more heat energy, some of them will vibrate so hard that they will start moving past each other. This means that they have acquired so much energy to overcome the forces holding them in one place. The particles are still touching each other, but are moving past each other and are not arranged in lines. What happens if you add more energy? The particles move around faster and faster. Some of them get enough energy to overcome the forces holding them together. They escape from the liquid. They then become gas particles. Should I stop there?
That's why we stopped, Mr. Chakoni. So
Okay.
maybe we had also named the movement energy they are talking about there. We had given it a name. I don't know that there is any lady who remembers what that name was.
Charity, you unmute and tell us that name.
Okay.
Yes, Charity.
She's correct, but she's very soft.
I didn't hear anything.
Kinetic energy.
Heat energy. Okay.
Hey. What was the name? Can you be louder and tell us the name? We gave that.
Where have you gone?
Kinetic energy.
Kinetic energy. That was the name.
Okay.
Okay. So that's
Kinetic
where we
energy.
stopped, Mr. Chakonye, I think.
Yes,
There
sir.
were questions to answer there. I don't know whether those are, because below we still have changes of state. We continue.
Yes.
I don't know if they first answer these questions because we never answered them.
We
But
can go through them quickly. Let's go through these questions very fast and then we move forward to the next stage. Okay. We can see question number 1 there.
The first exercise, they were supposed to perform it in class, but they're not in class. I don't know if they can play with their siblings.
Yes, perhaps, but
they can include their siblings. That is in case there are many.
That's the thing. It requires numbers.
Sibling, you're in trouble.
It requires numbers, so
yes,
we leave that to them because they can read. Hopefully, they have got a copy of these notes. So let them read through that and try to do that role play. But I think let's focus now on that exercise because certainly we can't do much with that here.
Okay.
Okay. So question number 1 there, guys. Yes, maybe again somebody will read this because I'm sure there's somebody out there who can read this. 3 participants' hands are up.
Okay, let's have Nachi Gude Gladys.
Gladys, read for us that.
Okay, question number 1. We learned that matter is made up of small particles. Give some experimental observations that show this.
Explain.
Okay. Matter is made up of small particles. Experimental observations that show this. We've gone through this in the previous lessons. What are some of those things that we talked about, those experiments or scenarios that we saw that seem to suggest that matter is made up of tiny particles? Somebody say something here.
Chirabo, Hope.
One of the experiments I remember is when you fill a balloon with air and you leave it in one place for some time. When you come back, you find that the balloon has reduced in size because the particles of air have escaped through the rubber skin.
Okay, thank you very much. The particles of air are so tiny to the extent that they will be able to escape through those pores that are not even visible to our naked eye, and consequently bring about a decrease in the size of the balloon. Thank you very much. Any other observation? Any other thing that any experiment that you talked about?
Tamal, your hand is up.
The movement of dust particles when they are raised into the air.
Absolutely. Thank you. That's another wonderful one. The particles of air are too tiny to be seen by the naked eye, but we are assisted to know that they exist by looking at the dust particles, which are visible, moving about, not moving about randomly and continuously. So that means that the air particles which are bring about their movement, because they continually hit them, are much, much smaller. So that's another very good evidence for the existence of tiny particles of matter. Okay, any other?
Crown.
Ink. Okay, the experiment of ink in water.
Experiment of what?
Ink in water. It shows
Okay.
that water particles are tiny and
Water particles are tiny. Okay. That is correct as well. When you put ink in water, you see the ink particles spreading, moving to all parts of water. That means that what makes them to move again should be the water particles because of their continuous movement. Then there was also that of potassium permanganate, another one of tea leaves. I think all these point to the same direction. So thank you very much, girls.
But they have forgotten a very important one. Mr. Chakoni, it is a very important experiment they are still forgetting. They have not made mention of it. I don't know that anybody remembers it. It has a very Brownian name.
Okay. The one that
which experiment is that?
Where pollen grains are put in water?
No, this is it involves the smoke cell.
Yeah, it's the same thing. This one in liquid, the other one in water, in air.
Then there is another one which is about to
gases.
The gases, yeah. Where we use that very funny gas, I forgot its name, but let me just show you that gas there.
Ammonia. It's ammonia. What is it?
What name? Bromine gas.
Okay.
Those experiments are quite crucial because the question is asking what experiments. Is that okay? Gives experimental observations. Top of the list should be Brownian motion experiment and then the bromine gas experiment. Then the others are observations that are naturally occurring. That is the spreading of the gas, I think dust. Then there are small particles that usually get stuck on the windows and so on and things like that. The movement of smoke in the atmosphere. Yeah, those were related to diffusion. And then the movement of ink in water.
Okay.
So I think the experimental observations, they have to limit them from naturally occurring naturally occurring scenarios to experimental things that can be done in the lab.
Okay.
Yeah. So Brownian motion, girls, there is Brownian motion, there is the bromine gas where you have the gas jets. Okay, there is the ink experiment, the spreading of ink in water, and then maybe you can include tea leaves. Then the other ones are things that occur naturally in the atmosphere, the rising of dust and so on. Okay. Yes, please.
I have a question, but it's not what we're talking about. It's about the previous lessons we're learning. It's just one question. I was just asking, does Brownian motion take place when diffusion is taking place? I just
When
need
what?
confirmation with that. Does
When what?
Brownian motion of particles take place as diffusion takes place if it's in gases? Do they
As
take place
diffusion
at the
takes,
same time?
the Brownian motion experiment is strictly about the random movement of bright particles that are observed in a confined cage. So this one is not about diffusion now. Diffusion, there should be free movement from one area to another, but this one is a confinement. All we see are particles that are darting around, but diffusion in most cases occurs in free space.
Okay, so Brownian motion doesn't take place as diffusion takes place.
Diffusion is actually a result of the movement that has been demonstrated by Brownian motion.
Okay.
You understand?
Yes.
Brownian motion demonstrates the movement. But what does that movement cause? The movement shows us that actually diffusion can take place.
Okay. Thank you.
Okay.
Excuse me, teacher.
Yes, please.
The examples, I think it was you who gave them. The examples you gave were like the experiment of Romaine gas, then also you said Brownian motion, then you also say diffusion. But when you say Romaine gas, it's part of diffusion. So do you have to also mention diffusion again?
Okay, in Brownian motion, it is demonstrating movement of gas particles from an area of high concentration to an area of low concentration. So there is movement. Can you listen to me? There is movement of particles from a region of high concentration. So that implies that the particles are moved from one point to another, isn't it?
It does.
Now, how do they move? They have a tendency of moving from regions of high concentration to regions of low concentration. Now, listen very carefully. The particles here, we have particles of a gas that are in the atmosphere or free air. Are we together? A particular gas, like, let me put it this way. This is what we observe, that if you open a tap, what gas are you opening? What are you releasing into the atmosphere? If you open a gas tap, you are, yes, that gas, that flammable gas now starts, and you start smelling it into the atmosphere, isn't it?
Yes.
So diffusion basically refers to a certain type of gas that has been released into or immersed. Remember, we talked about we immerse a certain concentration into the atmosphere or into another fluid, and then we observe the smells, the perfumes, and so on.
Yes.
Do you get the point, by the way? You have introduced something into free space.
I understand diffusion. I was asking about number one. I was saying the questions were answered. I was saying for number one, do we just say diffusion and Brownian motion, or we have to give the experiment for Brownian motion? Because teacher gave us examples like diffusion, Brownian motion. Then he also said ink in water.
But Mr. Chakoji, the girl has a point. We learned that matter is made up of very small particles. Give some experimental observation to show this.
I don't think it's okay if you just say diffusion and Brownian motion. I think you have to give examples.
And I think the examples are the ones that the girls were giving, because they brought out the real examples, but they did not focus so much on the name of the experiments. So I think yes.
Okay.
What are you saying you should give?
So those were the examples, like the spreading of ink in water. That is actually diffusion. And then Mr. Job is saying, but why is this diffusion coming about? It's also coming about partly because of Brownian motion, because of the movement, that random movement of the particles. The particles of water are also there. But then you also have that movement from a region of high concentration to a region of lower concentration. So which is actually diffusion. So I think that there was that other girl who was asking that, can diffusion happen at the same time as Brownian motion. We may not be able to alienate the two processes in an environment. The two could actually happen. You can have the diffusion happening at the same time. Yes. I think that we've done justice to this one. Maybe we could now go to number 2. You're welcome.
Excuse me, teacher. By using the idea of moving particles. Yes, please.
Teacher, so what exactly should we write? Should we write the experiments or the observations we make during the experiment?
Okay.
I think all the answer
it's okay. Go ahead, Mr. Senjobe.
No, Mr. Chako, you can go ahead. But all the experiments that we mentioned are correct.
Exactly.
The movement of gas, the movement of dust in the atmosphere, the Brownian motion, the whatever, all those demonstrate that particles are made of matter is made up of small particles.
Exactly. Okay. So I hope that is clear to that girl who was seeking clarification.
Excuse me, teacher. So when we are mentioning those answers,
when what?
When you're mentioning the answers, should we like explain them?
The question says, give some experimental observations.
That is like state.
State. So just say diffusion.
So teacher, there are two major answers, Brownian motion and the
diffusion
paper experiment.
Yes.
Okay.
Those can do for now.
Okay.
But later on, when you move on, you find that there are other things also as we advance. The other things that we shall talk about in due course. Okay. So number 2.
Machikude has a hand up. Machikude has a hand up.
Teacher, I wanted to give the answer to the second question.
At what?
So let me read it.
Okay.
Explain the following observations by using the idea of moving particles. Question A: wet clothes hang on a line become dry even in cold weather. I think the answer is that the liquid in the cloth escape into the air.
Okay. Okay. Explain the following observation. Okay. The clothes will dry even in cold weather, and you are saying that the liquid in the cloth escapes to air. I think that is correct, but you might also want to give us a name of that process. Can you name that process also? Hello?
Have we done that process, Mr. Did we give it a name?
I think it will actually come out specifically, I think, in the subsequent section there. In the next section coming through. But
we'll come out in the next section.
Yeah, that's what
I think for now, let us leave it at that.
Okay. So that answer is definitely correct then. We'll then move on to part B. Part B, somebody to read part B for us?
Excuse me, teacher.
Yes.
Could she please repeat her answer? I didn't get it.
But you also need to be attentive because we don't want to keep moving back and forth because we always have a time constraint. Okay. Somebody, could you please repeat your answer, previous speaker?
Yes, teacher. The answer was the liquid in the cloth will escape into the air.
The liquid molecules,
Yes,
the liquid molecules will escape into the air.
Okay. All right.
Excuse me,
so
teacher.
Did you hear my friend?
Excuse me, teacher. How about if you said the particles in the liquid will escape into the air? Is that the same answer?
The particles in the liquid.
Yes.
It is wet clothes. What
you have a wet cloth?
Wet clothes. What makes the clothes wet in the first place?
The water.
Yes, so it is the particles of the water that are escaping. Isn't it?
Yes.
Yes, question.
Is it by evaporation?
Okay, for you are
Okay.
correct. It's by evaporation.
I'm asking because the chemistry teacher told us evaporation can happen even in room temperature. So
And we are saying you are correct. For us, we
You are
have
very
not
right.
yet named that process, but it is very correct. It is by a process called evaporation.
Exactly.
okay,
So,
thank
so they are bringing in knowledge from other areas, which is very good also. Cross-cutting
Okay.
issues. Okay. Do we need to continue on that with that one, Mr. Senjo? I think we can move
No,
ahead.
that is that. We will go to
Okay.
B.
If you put some sugar in tea, the tea will become sweet, even if you do not stir it. Yes. Somebody tell us, what do you think brings about this? Tea put in sugar, or rather, sugar put in water.
Excuse me, teacher.
Please go ahead. Is that a computer? Please go ahead.
Teacher, it's Dendo. I wanted to ask that I had done this work and my answer was like on cold days, the water in the wet clothes freezes and supplements into water vapor, and this leaves the clothes dry.
No, that answer is not okay here.
Sublimation is a sudden change from solid to gas.
Yes.
So sublimation was a long process at a long time.
Okay.
It was talking about two states that are not happening here. So you rather say evaporation and the water molecules escape into the atmosphere. That is all. Whether it is cold or not, because evaporation takes place at any temperature. That's why they are putting there dry or cold weather. It doesn't matter. Evaporation will still occur.
Because it happens at any temperature. So Eliana's hand is up. Eliana? I saw Eliana's hand up. Okay, maybe she's giving up. Let's go to
what happens to sugar girls?
For the sugar, I wrote the sugar will diffuse in the tea.
You put sugar, you don't stir, but the tea still becomes sweet. What happens? Explain that.
I wrote that the sugar will diffuse in the tea.
Diffusing? You say diffusing. Yeah, that is very correct, I think. That is the correct answer.
That is by diffusion. Okay. So then we'll move on to part C.
Excuse me, teacher.
Yes.
About if you say the sugar dissolves in the tea, is it correct?
Dissolves. It simply means it disappears.
Then what happens?
Then what happens? It could dissolve and stay in the same place. But the water eventually becomes sweet. So without stirring. Because dissolving could make it disappear but stay in one place, concentrated there. But now we are told the whole water actually becomes sweet without even stirring. So diffusion surely is
the correct answer. This is spreading from high concentration to low concentrations.
Exactly.
Okay.
Excuse me, teacher.
Yes.
Yes.
How about if you phrase your answer in this way that the sugar particles diffuse in the water?
You are going to change the language. You are the same thing. Thank you.
Okay.
The answer is diffusing, please. The sugar will diffuse into the tea or the water. Okay, that is all.
Teacher, what about teacher, I wanted to read the next question and I give my point of view to it.
Yes.
A car tire is full of gas, air, but the part of the tire underneath the wheel does not look flat. My idea is that the molecules of the gas do not, they collide with the molecules of the car tire, so they will not they will collide with each other. So the gas molecules will not diffuse with the molecules of the wheel. So the wheel will stay, it will not become flat.
Okay, that's your input. Thank you.
Teacher.
Can we hear from some other person?
Teacher, how about
Yes.
if you say that since particles in gas are far apart, when they are put into that car tire, they spread out and enabling the car tire to swell and not look flat. That's what I think.
That's what you have given us. Okay, we shall harmonize at the end. We've had your response. Thank you. Anybody else to tell us what happens there? Why that observation is happening? Azel? Azel? Say something?
Yeah.
Teacher, can I try?
Yes, please.
My point of view is the particles in the car wheel are closely packed, hence the gas particles won't have any walls to escape.
Repeat that answer. You say the particles of what?
The particles of the car wheel are closely packed, hence the air particles inside the wheel will have no space or walls to escape.
Can I give you my answer?
The problem is that the wheel, the particles of the wheel, that's where the problem is.
Yeah.
Okay, let me ask you girls, you get a balloon, yeah? Okay, let's imagine that we have a ball in which we are putting air inside the ball. I believe most of you play basketball, football, etc. Suppose you keep pumping air into this ball, what happens to that ball?
It bursts.
Burst. But you pumping air into a ball so that it bursts, or you have what happens?
The pressure pushes the walls out.
It pushes the walls out. Suppose you try to squeeze that ball.
Teacher. Yeah.
Too hard to compress. It will be very difficult to.
It will be very difficult to. What do you think happens?
To compress
what
the
happens?
ball.
What makes it very difficult to compress? Yeah. What have you pumped into the air, into the ball?
You're pumping air.
You are pumped in air. The more air you pump in, the harder it becomes to compress the ball, isn't it?
Yes.
Isn't it?
Yes.
So it is like getting you and I say, I'm going to squeeze these girls of S1 and all the S1s, I pack them into one class. What will happen? You imagine a situation where all the S1, whatever, all of them are packed into one class. Will you have movement space?
No.
No, we shall not.
What you will be overcrowded, isn't it?
Yes.
Yes.
So that is exactly what happens. Now, can you try to describe? Suppose you pump a car tire and you make it full of gas, and then you try to squeeze it because the car is trying to put its weight onto the car tire, but the car tire almost remains, I mean, as though it is not feeling any whatever. So can you explain that now? I think you have got a better understanding.
Okay, teacher.
Air inside. Sorry.
I think the tire is filled with a lot of air, which has spread out the whole time. That's why it doesn't feel flat. And
it almost becomes incompressible. It is that answer. What together?
Yes.
So the car tire, the molecules of the gas are so closely packed that they almost become incompressible. Is that okay?
Yes.
So, Mr. Enjobe.
Excuse me, teacher.
I think we may be constrained to also use the term pressure. That is a lot of pressure because of that high compression.
Because of that high pressure.
Yeah. So there's high pressure there. That means that there are so many particles there in. and it is uniform within the tire.
Yes.
It is uniform within the tire because you cannot say that it is too much on the lower side or on the other side. So it is uniform throughout, hence the shape of the tire remaining this,
Almost the
kind
same,
of.
unchanged.
Yes.
Is that okay?
Yes.
Okay.
Okay.
Teacher, could you repeat the answer for pressure?
Mr. Chakoji, why I wanted to avoid that word pressure?
Indeed.
I wanted to use that there's the air molecules become overpacked. So that they become almost, because I think that's the information that they have.
That is true, but
Because
they have
we are
also
talking
used the word
about,
pressure. Before, you remember when we were talking about to dense and what have you, that word seems to be crossing their minds. So that's why I was really.
That's why you brought it in.
Me, teacher.
Yeah, because,
yes, please.
May I give the answer?
You give the answer.
The air particles are too compressed, so that's why the car tire doesn't look flat.
Mr. Chakonya, I think at their level we better leave it at that.
Exactly. Let's leave it at that. Further understanding will continue.
We'll bring in pressure
as we acquire more and more knowledge. Okay. So there is part D. Somebody to read for us this one. Nachigude's hand is permanently up. Nachigude. Nachigude, read for us that part D.
Yes, teacher. It says, if you place a balloon over the top of a test tube that contains water and you then heat the water, the balloon blows up.
Okay.
Teacher,
yes, go ahead.
Okay, for me, teacher, I think that the vapor from the boiling water will okay. Teacher, I think that the boiling water will expand, will become a lot in the balloon, making it to burst so that the vapor can find its way out.
Beautiful answer there, Nachigude. Luis, you want to supplement?
Yes. Can you say
the balloon? Let us understand that question. The balloon blows out. It does not actually talk about bursting, but the balloon, the size of the balloon increases. I don't know if you get the point. It is like you're blowing in air, so the balloon starts bulging. You understand what I mean? That's what they're trying to tell us.
Yes, but
that one has a proper answer that when you heat water, what forms?
She talked of vapor coming out.
The vapor enters into the balloon and the balloon starts to do what?
To blow up.
Blow up. That is what happens.
expand?
Okay, expand or whatever the case may
but
be.
if it continues progressively,
if it continues, it will burst. But this question is very, very specific. It is not talking about bursting. It is just increasing in size.
Yeah, but I think the bottom line, Mr. Senjove, I think the bottom line is the escape of vapor from the water, or particles of going into that space, and therefore making the balloon to gain size. So that process there is probably what the question is emphasizing.
Excuse me, teacher.
Yes.
Can you say that the air molecules inside the balloon expand when it is heated?
No. They are talking about the water. You are heating the water.
Teacher?
So we don't have evidence that
you heat the water, and what happens to the water when you heat it?
Teacher?
The vapor.
I think that vapor cools.
The vapor starts filling the balloon. Is that okay? The vapor that escapes from the water starts filling the what?
The balloon.
And the balloon blows up. That's basically what they want.
Yes, because there is no evidence that that balloon initially contains air. It may not be having any air in it. It is just covering the top of a beaker, whatever it is. So it must be the vapor that is really bringing about that bulging. Okay.
Excuse me, teacher.
Yes, please.
May I Please repeat the answer for part C. I lost connection.
Oh, the car tire. Somebody repeat for her the car tire. What happens when you blow in too much air into?
The gas molecules are too compressed, so the wheel does not move flat.
Okay. So that's what I think we said for part C.
Okay. So, Mr. Senjobi, are we done with this one? I think we are.
We are done with part D.
I see Kayesu and Kaitesi's hands up. I wonder what their concerns are or they have. Okay.
Teacher, on C, could the idea of air exerts pressure also be correct?
Certainly, it is a very correct one.
Correct, it is the very correct one.
Question.
Okay, thank you, teacher.
The air exerts a lot of pressure on the tire walls and that stops the tire almost from becoming flat. That is also correct.
Okay, so change of state. We are now on change of state. I think this is what we started off with. That
Excuse me, teacher. Do you mind if you increase the volume of your gadget, because I can't hear?
It is
volume is maximum.
It is you to increase the volume of your gadget so that you can hear.
My God, I've increased.
For us, we are at maximum. We are at peak. Oh, what is the other name?
The pinnacle of the volume. Apex, kind of.
Okay. Actually, we have done most of this, but they can just read through the notes and we move away from here.
Absolutely, absolutely. We've gone through this in that discussion we've had. So let's get somebody to read for Apio. Apio Grace, she's lowered her hand. Queen Victoria.
Teacher, should I start from changes of state?
Absolutely, start from there.
Changes of state. Many of the users of the different states of matter rely on their changing from one state to another. For example, purifying water relies on the change of state from liquid to gas again, as does the formation of rain. The burning of a candle relies on the wax changing from a solid to a liquid and then to a gas. Understanding that when things change from one state to another requires energy, heat, gain or loss is very important. Substances can move from one state to another when specific physical conditions change. For example, when the temperature of a substance goes up, the particles in the substance become more excited and active. If enough energy is added to a substance, a change of state may occur as the matter moves to more active state. The particle model will help you to explain how substances change from one state to another. An example of this is the changing of ice, solid, to water, which is in liquid, and finally to water vapor, which is in gas. Look at the diagram in figure 3.11. Explain what happens to arrangement of particles and forces holding together when energy increases at every state. Do the same to explain what happens when heat energy decreases at every state.
Okay.
That's the diagram. That's the diagram, Mr. Chikoni. That is the diagram 311.
Yes. Thank you very much, Mr. Senjobe, and thank you very much, our reader there. I think we have heard loud and clear, and we can also read for ourselves what she has just talked about, that to change from one state to another, you really need an input of energy. There is need for an input of energy. So this is what we have been discussing really, that if you have a solid, for instance, and you apply heat to it, what happens to the particles? The discussion started from there at the beginning. And I think somebody quickly said, because I can see it's 10 here, almost 10. Somebody told us that when you apply heat to a solid, the particles of the solid absorb that energy, heat energy in this case, and consequently vibrate more aggressively, also move further apart, weakening the forces of attraction between them. Consequently, this until a situation will come about if this process continued until the particles really are no longer able to come back and vibrate, but rather now start moving freely. That means that we are now moving from a solid state going to liquid state, and somebody gave us a name for that process at the beginning, that process being called melting. But then they have also told us that what happens if the reverse is done? If you absorb heat from this solid or from this liquid now, what happens? So people, maybe somebody could tell us, if a liquid is put in a fridge, the fridge does the opposite now. It takes the heat out of the liquid. What does that lead to? And what's the name of that process? Quickly, as we really finish up this.
It leads to freezing.
Yeah, it's freezing.
The process is called freezing.
Freezing.
So therefore, freezing is the opposite of
melting.
melting. And the two processes, do they happen at the same temperature or different temperatures?
Different temperatures.
At different temperatures.
Different temperatures.
Yes.
Is there anybody with a different view?
At same temperatures.
At the same temperature.
The temperature is the same.
Same
Okay. If you're talking about ice or water, what is the melting point of ice?
0 degrees.
0 degrees.
0 degrees. And what is the freezing? The melting point of ice actually is 0, and the freezing point of water is
0.
also 0. So it's the same temperature, only that it has different names depending on which side you are moving. If you are moving from solid to liquid, we call it melting. And if you're moving from liquid to ice, we call it freezing. Okay?
Yes.
But the temperature has a value of 0 degrees Celsius. And now going forward, if you apply more heat to a liquid, what happens? Somebody told us a name there. Conversion from liquid to gas or to vapor. What name did somebody give us earlier?
Evaporation.
Evaporation, indeed. Okay. So again, how does this happen? I think we have just had, again in the previous discussion, that as you heat a liquid, you have the liquid molecules or particles escaping into vapor state, and that process is what we refer to as evaporation. At what temperature does this happen, members? Nakalema, say something.
100 degrees.
100 degrees.
Mr. Chaponi.
Yes, sir.
Let us correct something. There are two processes. Listen, girls, there are two. If you look at the diagram, a liquid can change to a gas via two processes. One is called boiling, which takes place at a fixed temperature. But the other one is a continuous process called evaporation. That one does not matter. It doesn't matter whatever the temperature. Have you seen that? Yeah? A liquid can evaporate at any temperature. A liquid can boil at a specific temperature. For example, you boil water at what temperature?
100 degrees Celsius.
At what temperature does the water evaporate?
Any temperature.
So you must know the two processes by which a liquid changes to vapor state. One is boiling, whereby you have to put in a lot of heat. And I think you know that boiling is far faster than evaporation. Is that okay? Now look at the reverse processes in that diagram. There are some names you are missing. What is the other name for freezing?
Solidifying.
What is the other name for condensing?
Liquefying.
Maybe we may use those names. Is that okay?
Yes.
Okay.
Okay.
Mr. Japonyi, please, you can.
Yeah, definitely.
Wind up.
I don't think we have a lot of time here, but yes, I think that should be able to wrap it up. That you are moving from a solid, from a liquid to a gas, and this could happen in two processes, as Mr. Senjobe has really emphasized. You have a process happening at any temperature, when you mop your room, the floor will be wet after mopping, but after a short time, you find the room, the floor actually looking dry, without any input of heat. And also earlier on, we saw that a wet cloth, even on a wet day like now, really that cloth will eventually dry up. So there is no heating happening here, and this is happening by a process referred to as evaporation, which can happen at any temperature. And then there is another way you can have a liquid go to vapor or gas, which now we refer to as boiling, which now requires an input of heat. And for the case of water, it happens
100 degrees.
Mr. Chairman. Okay. Okay, we are winding up, girls. I think we have got the point.
Yes.
There are some questions which we shall be answering later as we wind up that, but I don't know what time we shall have for this. Maybe our next lesson. But look at that. I want you to take a picture of those questions. Do whatever is within your means to take those questions down, and then we will answer. You will give us answers.
Yes.
Girls, also prepare for a test. We are winding up, and I think you know that you have a certain form of evaluation for what we have covered. Is that okay?
Yeah.
To read
So
through
when will they start? What's the specific day they will start?
Oh, it will be communicated as we make a timetable. After the timetable is done, we shall communicate, and then you'll know, but prepare for that evaluation. But it's specifically all about only what we have covered in these interactions online.
So is it going to have a variety of topics, or is it going to be one particular topic like the activities of integration?